Is September 25th, and we are going to talk about sections 3.4 and 3.5 in the textbook. And what we're discussing is the design of transmission shaft. And when we're talking about transmission, what we're talking about really is the transition of power. Almost always. Sometimes we're just getting something to rotate at a different rotational speed. However, the main reason for this type of a transmission when we have a gear train is the transmission of power. So basically what we find is that if you have a power transmission shaft and you subject it to a torque, and it spins at some angular speed omega, which is in radians per second, that the power that can be transmitted by that shaft is equal to the torque times the angular speed. And everything here, these are really vector quantities. But if you think about it, everything is very defined. If you have, this is the good news, this is the difference between physics and engineering. We all know the directions. If you've got a shaft and it's spinning this, if it's hooked onto something, it's in the x-axis, the torque is in the yz plane, everything is good. So our directions are well defined, and we do not have to worry too much about the vectors and the directions because of the geometry of the actual system. So if you take a torque, which is in dimensions of force times a distance, and you multiply that by omega in radians per second, we know that, I should put time, okay? We know that radians are actually dimensionless, and we have a force times a distance per a time, which is a unit of power, okay? So in other words, a force times a distance has the same units as energy or work, and per time, work per time, is power. So if you have a force, a torque in, for example, Newton meters, and your time is in seconds, the power is going to be in Newton meters per second, which is a joule per second, which is a watt. Okay? And if you have a torque in foot-pounds and power and omega in radians per second, you get a foot-pound per second, which is not, this is a base unit. It doesn't have a particular name because it's very, very small, but 550 foot-pounds per second has a unit of a horsepower. Does anyone know where the units of horsepower came from? Because once again, when we talk about the U.S. customary system, we always have to figure out what the heck why the heck we are talking about these weird units. Anybody have any ideas about that? Well, it comes out of our agricultural history, okay? And back in the day, what happened is people used to farm with horses, of course, and when moldboard plows came out, and when tractors that would pull a plow came out, the unit that farmers were interested in was how many horses can this tractor replace. And so if you look at a John Deere tractor, for example, and you look at the power rating, they'll always be in horsepowers. And back in the day, I believe that the John Deere Bs, some of the first ones that came out with, had ratings of about 15 horsepower, 12 horsepower. And that was basically telling a farmer that would pull a plow through the ground at the same rate as it would take a team of 12 horses, which of course 12-horse team is unmanageable, but that's another story. So anyway, but this is not exactly the same as like if you have a car and the car is rated at 200 horsepower. It doesn't really mean that you could pull the car at that particular, that you would take 200 horses to pull the car, because we're looking for some different quantity, even though they're both power. But if you look at force times distance per time, another way you can think about that distance per time is velocity, isn't it, or speed. So when we talk about cars, we're really more interested in this velocity piece. When we're talking about a farm implement, we're talking about generation of force over some particular distance. So they have the same units, and they're very strongly related to each other, but they're not quite the same. So if you look at, even today, if you look at power ratings on tractors, like the power takeoff, the numbers seem low compared to what they would be for cars. So it's just a little bit different. It's like, even if you look at a lawn tractor, like my mother-in-law has a lawn tractor, I think it has a 15 horsepower rating or something like that. And what that means is it's going to chew up shrubbery pretty quick. So that's what you're getting at. So it doesn't mean you're going to be able to take it down the highway at a particular speed. So they're related, but not exactly the same. All right, so now that we've discussed sort of the basic units, also a watt is very, very tiny in terms of power generation. So we often talk about kilowatts or megawatts. Okay. This is not 555, it's 550. I don't know, I just got carried away writing fives there. So there we go. All right, so we know that power is equal to torque times omega for this type of when we have a spinning shaft. It also turns out that omega, which is in radians per second, is also equal to 2 pi times f, which is a frequency. And so since 2 pi is the number of radians per revolution, a frequency is usually measured in revolutions per second, or sometimes you'll see revolutions per minute, which are RPMs. Okay? So the basic point is there may be a little bit of conversion math to do here. So we need to get this quantity. If we have a frequency, we basically need to get it dimensionless, remembering that radians are dimensionless, because revolutions are not dimensionless. Okay? So there's other cases where you may have seen RPMs. If anybody listens to vinyl records, anyone know what records spin at? Yeah, 33 1/3. I don't know why, but so anyway, so an LP spins at 33 1/3 RPM. So that's the deal on that kind of a thing. All right, so that means that we can also write power. Since we know omega is equal to 2 pi f, we can say it's torque. This is awkward. I always should write it this way: 2 pi times the torque times the frequency. That's how much power you can put through a shaft given a particular rotational speed and a particular torque. So an RPM is a rev per minute. A rev per second is also called a cycle per second, which is called a hertz. Okay? So in other words, 1 RPM is the same as 1/60 hertz. So that about gets all of the conversion factors that you need to know. All right, then the last thing is that we're going to talk about in Chapter 3. We said that we're only going to look at power transmission shafts that are cylindrical, or we're only going to look at any kind of torque on any kind of a shaft that is either cylindrical or a hollowed out cylinder. And there's one other sort of characteristic that we need to look at, which happens sometimes, which are called stepped shafts. And a stepped shaft just means that we have a larger part of the shaft, and by larger I mean a bigger radius shaft. stepped down to a smaller radius shaft. And step shafts occur in a lot of different designs. And once again, we have a fillet that steps from one to the other. Really, when you have anything like this, and we talked about this with the flat bar with fillet as well, but if you step here, if you step with a hard corner, you always have a real tendency to breakage at that point. So the filleted step is a much sounder design. And so that's why you see them all the time. Generally speaking, that fillet will have a circular, it goes from a straight edge to a circle, through a circle to another straight edge. And so if we have a step shaft, you'll have stress concentrations that will occur. And much like we said before that tau max for a cylindrical shaft is equal to T times C over J, or that tau is equal to T times, wherever you are, rho is what they called it, over J. For a filleted shaft, we just use a concentration factor, just like we did with the flat bar with fillet. Right? So we find the concentration factor K using charts, and the two geometric factors that we need are the diameter of the larger part of the shaft and the diameter of the smaller part of the shaft. We find this ratio, and then we find the radius of the fillet divided by the smaller part of the shaft. And then we can find our K factor, our stress concentration factor, using a chart like here. This is on page 188 of your textbook. So the process is very much like we did with the flat bar fillet, or the flat bar with a circular hole in it. Basically where you find the R over little d ratio, and then you come up to the line that represents the capital D over little d ratio, and then you just come over to the side and read your K factor. So you can use the same equation that the tau max is equal to TC over J, only then you multiply that value by that stress concentration factor, so that you design so that your step shaft is going to be strong enough to hold whatever torque you put through it. All right, so do you guys have any questions at this point? All right. Well, let's take a look at a couple of problems. Always fun. So let me look at, this is good because we get some conversion factors. Problem 364 in your textbook. It says determine the maximum shearing stress in a solid shaft of 1.5 inch diameter as it transmits 75 horsepower at a speed of, the frequency equals 750 RPM. And then part B, I will leave for your homework. It's the same stuff except you have a different frequency. All right, so how do I find tau max when I'm given power and a frequency? So I know how fast it's spinning, I know how much power I'm putting through the shaft, and I want to know how much what my maximum tau is going to be. All right, so here's the way it works. Tau max, we know, is equal to TC over J. We know that because this is a solid cylinder, that my J, or my first polar moment of inertia, is equal to 1/2 pi r to the 4th, which is C. So you can see that for a solid cylinder that this C will cancel one of these, and this will flip up to the top. So I get that tau max is equal to 2 times my torque over pi times C to the 3rd. All right. Well, I also know from what we've just learned today that power is equal to 2 pi times F times T. And since my T, or my torque, is unknown, but I have my power and my frequency, if I can resolve my units in this equation, I'll be able to solve it for torque. Okay. So my power is 75 horsepower, and we got to know right off the bat that will never do, right? I know that I have 1 horsepower per 550 foot-pounds per second. On the bottom, I have 2 pi times my frequency because I have to convert this into radians per second. My frequency is 750 revs per minute. So 2 pi is my number of radians per rev. So that's good. But I have minutes down here and I have seconds up here. So I need to convert that. I know that there's 1 minute per 60 seconds. So I've canceled these. My revs cancel, my minutes cancel, and on the bottom I have radians per second, and I know that radians is dimensionless, so I have seconds in the denominator of the numerator and seconds in the denominator of the denominator, so I am left then with torque in dimensions, or in units of foot-pounds of force, which I've written backward. My horsepower canceled out, radians goes away, revs goes away, minutes goes away, and seconds cancel seconds. So I have torque in units of foot-pounds, and that is a good unit for torque, isn't it? All right. So let's do the numbers. If I take 75, multiply it by 550, divide it by 2, divide by pi, and then I have divide by 750. And now here I have 60 in the denominator of the denominator, so that actually flips to the top, doesn't it? I multiply by 60. So my number is 5,252 with some change, 0.1008 foot-pounds, if I've done my math correctly. So it'd be 0.1, this would be 55, 300 divided by, I think I got something wrong. You guys want to do the math for me? I got like, I feel like I'm off by a power of 10.
You get 545.
Yeah, there you go. That looks better. Thank you. Yeah, when I kind of ran the numbers after I did that, I don't even know what I did, but if you take 75 and divide it by 750, that should be 0.1. And 0.1 times 550 should be 55. Then, so I should have about 55 on the top. Then here, this is about 6 divided by 60, right? So that's divided by 0.1. So that should flip up as multiplying by 10. So I got that my number should be about 550. So when I punched it into my calculator, it came out to be 5,000. Something didn't look right. So thank you for correcting that for me. So that looks correct to me. All right. So I have a torque of 525.2 foot-pounds. I can use that in this equation to calculate my tau max. So I have 2 times 525.2 units of foot-pounds of force. Once again, I've written that backward. Divide that by pi times c to the third. This is a 1.5-inch diameter shaft. That means my radius is half of that, or 0.75 inches. Since this is in feet. Now, here's an interesting thing. What I'm coming out with here is a tau max, and a good unit for tau max is pounds per inch squared, isn't it? So I'm going to say let's convert this one to inches and leave this one in inches. So it will come out with units that will be interesting and applicable. So that means I've got inches down here. I need to convert this. I have 1 foot, 12 inches. So that goes against this. And then I have inches to the third and inches in the inches to the third in the denominator, inches here. So I'm left with pounds of force per, when I cancel this against that, that's going to be inches squared, which is a good unit for tau max. Okay, so let's see what my value looks like. 2 times 525.2 times 12 divided by pi, and then divided by 0.75 to the third power. And I get a value of 9,510.5, which is roughly 9.5 KSI. What do you get? Same? Yay. Okay. So I think when you do the part B of that, you'll be very happy. So 364 part B, because it will look exactly the same. It will give you a chance to run some of those numbers. Okay. I'm also going to ask you to do problem 369, which will, it's an SI unit problem, so you'll get to work with that. And then let's take a look at a stepped shaft. Okay. 3.69, and then 384 is the last one I'm going to have. So here, I'll put this up here so you can see. This is what your homework is going to be. 364 part B, 369, and 384. And I'll do 385, which is a step shaft, although I think you'll be very comfortable with the idea of the step shaft, but let's go ahead and work it out so that you have one in your notes. Okay. So problem 385 says we have a stepped shaft that rotates, so we have a frequency of 450 RPM. And knowing that the radius of the fillet is 0.5 inches, determine the maximum power that can be transmitted without exceeding the allowable shearing stress of 7,500 psi, right? And we're told that the smaller radius is 5 inches, and the larger radius is 6 inches. All right. So first we know tau is equal to TK, in this case TC over J. Okay. Now, one thing I want to point out, when you find J, the value C over J is going to be different for this shaft than it is for this, right? So if you think about it, in each case, on the smaller shaft, it's going to be 5 over 1/2 pi times 5 to the 4th. And on the larger one, it's going to be 6 over 1/2 pi 6 to the 4th. So in other words, this is going to cancel this. This is going to cancel this. And we're going to end up with 2 over pi times the smaller diameter to the third power, or 2 over pi times the larger one to the third power. This and this are both constants, right? So if we're looking for a maximum value of tau, we want to find out where this value is the largest or the smallest, right? So in other words, which one do we use? Well, we want to find the smallest torque, because if one of them breaks, or if we exceed it in the small or the large, it's been exceeded. So in other words, we want to find the smallest value of torque. So we want to know where this value is going to be the largest. Which one of these is going to produce that largest value of C over J?
2 over 5.
Yep, that one. That is correct. So in a stepped shaft where they're both cylinders, you always use the smaller part of the shaft for that calculation. Because once again, we're always talking about the weakest link in the chain concept. When it fails or is exceeded, it's failed or exceeded. Doesn't matter. It does not matter philosophically which one fails. After it fails, it fails. Okay. So this is the one we're going to use. So let's go ahead and I guess we could find our stress concentration factor. I'm just trying to decide what I want to do here. The other thing we could do then, since we're talking about a power transmission, we know this value, don't we? We can find this value and this based on the geometry. So we can use this equation to calculate the torque. So let's go ahead and do that in 2 parts. Okay, so we get this 7,500 psi, which is pounds of force per inch squared, is equal to our K value times our unknown torque times the smaller of these two, 2 pi 5 to the third, 5 inches to the third. And we need to find our stress concentration factor. So we go back to our table, and we have our 2 ratios. So just take a look right here. We need to find R over D, and we need to find capital D over D, and then we can use that table. Okay, so we're told that R over D is going to be 0.5 over 5, and that's 0.1, isn't it? D over D is 6 over 5, which is 1.2. So using those 2 values, R over D of 0.1, D over D of 1.2. See, we kind of go off chart here. So I would just estimate, see, this is, well, let's see, 1.25 right here, 1.6, 1.1. Okay, so it's in between here and here. That's about the best we can do. So we have between 1.3 and 1.35. So I'm going to say my stress concentration factor. Now, and if you choose a different value, as long as you do the process correctly, it's fine as long as you're in between the 2 lines, or your reading makes sense. I would say 1.325. Okay. All right. So I'll just get a new piece of paper here. .325. Okay, so then this is in inches to the third. This is in inches squared. Okay, so let's go ahead and work out the units here. We need to solve for torque. 7,500 pounds of force per inch squared divided by, because I'm going to solve for torque, 1.325, which is my stress concentration factor, is dimensionless. This is in the denominator, so it flips up to the top, times pi times 5 inches to the third over 2 is equal to my torque. Okay, now look at my units. This cancels against this, and that's inches. This is still 5 to the third. I have to get that value. But so I have inches squared, that cancels to inches. So I have pound force times inch. That's a good value for torque. I'm going to have to change it into foot-pounds or into another unit, but there's no reason that I can't work with that unit. All right, so let's do the math. 7,500 times pi times 5 times 5 times 5, which is 125, divided by 2 and divided again by my stress concentration factor. And I get a value of 1111415 inch pounds is what that amounts to. And let me know if that's what you get as well. Okay. Then we know that from our work today, that power is equal to 2 pi times frequency times torque. And in the specs of the problem, I was told that my frequency is 450 RPM. So I get my power is equal to 2 pi times 450 revs per minute. Okay, the 2 pi is radians per rev, right? So that goes away. But I have 1 minute per 60 seconds to get that to the right set of units. And then I calculated my torque as being, I'm going to just change this to divide it by 12, because I've got 12 inches per foot, and I'm going to get it in foot-pounds just because it's a big number. I'm just going to divide that by 12, and I get 92,618 foot-pounds. Okay? So I put in that value, 92,618 foot-pounds. And so revs go away, minutes go away, and I get foot-pounds per second, which is a good unit for power. I'll probably want to change that to horsepower in just a minute. But I take that value, divide it by 60 to get it to frequencies per second, multiply it by 450, and multiply that by 2 pi. And I get 4364527 foot-pounds per second. And then if I say there's 550 foot-pounds per second per 1 horsepower, I can divide that number by 550. And I get the power is 7935.5 horsepower, which seems extremely high to me. So I feel like maybe I have something off in my arithmetic. But I don't know what it is. So you have to check my numbers. But that is the correct process. And I guess it's not unheard of, but that's an awful lot of horsepower to put through a shaft. But then again, it's spinning really fast. So, 450 revs per minute. Pretty fast. All right, do you guys have any questions for me? All right, so you have 2.5 homework problems. And on Wednesday, we'll come back, answer any questions you have about Chapter 3. And then we will move on to chapter 4, which are pure bending moments. All right. So you guys have a great day. I'll turn off the streaming and we'll call it a day.